Inductive pump. Inductive pump is used to pump conducting liquids. In this example, the highly corrosive molten sodium is pumped. The principle of operation is the same as in linear induction motor. Eddy currents are induced in the conducting liquid and interact with the magnetic field and produce thrust. The construction is similar to the linear motor. We have the ferromagnetic stator, three-phase winding to produce traveling magnetic field. Instead of the rotor, we have a pipe with a conducting liquid inside. Our task is to calculate the force acting on the liquid and the joule heat in liquid. Okay. Let's start QuickField now. In QuickField I create new problem. Problem name is pump. Next. Problem type is AC magnetics. Frequency is 50 Hz, length units are millimeters, model class is axisymmetric. Winding connection is simple, so there is no need to add electric circuit to the model. I will specify the current in the winding. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. Here is the file and I will import it. The geometry is imported and you can see the cross section of the pump. In axisymmetric problems, the axis of rotation is a horizontal one, and we should draw only the upper half of the cross section. Here you can recognize conductors of the winding, pipe, liquid sodium and the core. In fact, magnetic field is distributed not only in these parts but also in the air outside. QuickField cannot simulate magnetic field distribution in the infinitely large space, so we need to restrict the simulation domain. Zoom out, switch to insert mode and draw the air block boundary. Here, change the line type to half arc and draw the half arc. Next I am going to assign labels. For labels I will provide material properties. Switch to select objects mode, click the object to select, and here I type in the label air. This is the liquid, this is the slot insulation, this is pipe, and this is conductor A plus, and this is conductor A minus, this is conductor B plus, and this is conductor B minus, this is conductor C plus, and this is conductor C minus. And we have to assign a label to the core. Click to select the core. That is all for block labels, but we should also assign labels to the external boundary. This edge will have label external. QuickField automatically assigns proper boundary condition on the axis of the rotation, so there is no need to assign label to the axis. Now let's provide physical properties for the labels. Double-click the label in the tree. Relative magnetic permeability of the air is 1. Pipe is made of non-magnetic material, again 1. Insulation is a non-magnetic material, 1. core is made of ferrite with the magnetic permeability of 200 and 0 electrical conductivity. Okay. The conductors are made of copper with a relative magnetic permeability of 1, and the current density is 6 amperes per millimeter square. In QuickField I should specify amperes per meter squared, so 6 mega amperes per meter squared. This is current density. Okay. In the conductor A minus, same magnetic permeability and the same current density with minus 6 mega amperes per meter squared. For the phase B, same magnetic permeability, same current density, but the phase is shifted by 120 degrees. For the conductor B minus, minus 6 mega amperes per millimeter squared, and again the phase is shifted by 120 degrees. C plus 6 240 degrees. C minus minus 6 240 degrees. Okay. I do not specify conductivity for the conductors because I'm not interested in the eddy currents in the winding. The winding is made of many thin conductors and the current density distribution is uniform. For the liquid I specify magnetic permeability, which is 1, electrical conductivity, which is 10 megasiemens per meter. There is no source connected to the liquid, so I left 0 voltage here. Okay. Far away from our pump, magnetic field fades to 0, so for the external boundary I specify 0 magnetic potential. Okay. That is all for material properties and the geometry model. I have only to build the finite element mesh. Just press this button, save all problem files and run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density distribution. Let's zoom in. Now you can see the eddy current distribution in liquid. Let's use the contour tool and calculate some integrals. Click to select the liquid, follow to the integrals, joule heat value 410 watts. The Lorentz force is 33 newtons, directed to the left. The force is caused by the interaction between the eddy currents and the magnetic field. I'm going to adjust the field picture, open field picture properties. I will switch on the flux density vectors, switch off the field lines, and change the presentation type to the momentary values. Okay. I will clear the contour so you can see better. Contour clear. Now let's take a look here. Here you can see that the current density value is positive, directed toward us, and the flux density is directed upward. Applying the right hand rule, we can find out that the magnetic force direction is to the left. Now let's take a look under another pole. Here we have a negative current density directed behind the screen plane, and the flux density vectors are directed down. Again, applying the right hand rule, I will find out that the force here is directed to the left. You can also switch on the animation of the field picture to see how the field varies in time. Okay, what else you can do here? I will stop the animation. You can use local values tool. Click any point and get flux density, field strength, current density and other field parameters. You can also specify the point coordinates manually. You can also use the contour tool to draw the arbitrary lines or arcs or select the existing edges. For example, here I will click to select the axis of the rotation, open the XY plot, change the value to the flux density. I'm interested in the Z component, the horizontal component only. Here is the flux density distribution along the axis of the pump, and if I change the phase, you will see the traveling wave, and the exact numbers you can see in the table. Coordinates, flux density vector components and other field parameters. In AC magnetic problems you can switch between the momentary values, root mean square and the peak values. For example, here I change to root mean square values, and the same I can do in XY plot and in the field picture. If you search for the inductive pump on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.